Welcome to the physics class BSc third semester, paper name Geometrical and Physical Optics, Electricity 1 and Basic Electronics. In unit 3rd, Theory of Dielectrics and Moving Coil Galvanometer. In the session 8, we learnt about boundary condition at a dielectric surface derivation. So first we seen about an boundary condition at a electric vector D. The boundary conditions are used to know how the field vectors E and D changes by passing between the two interfaces of two mediums. Cylinder is a Gaussian surface. Here the diagram this cylinder will be acts as a Gaussian surface, and E1 and D1 are the electric vector and the electric displacement vector of the first medium, and the epsilon 1 is the relative permittivity of the first medium, and the second medium having an electric vector D and the electric displacement vector D2. E2 and D2 are the electric vector and displacement vector of the second medium, having an epsilon 2 is an relative permittivity of the second dielectric medium. Here xy plane, x plane is the boundary between the two dielectric mediums. This is first medium of the dielectric, this is second medium of the dielectric. These two mediums are separated by an xy plane at absolute permittivity, having an epsilon 1 is the first medium and the epsilon 2 is the second medium. Then theta 1 and the theta 2 be the angles between the normal boundary and the field E and D in the medium 1 and medium 2. Now the cylinder is a Gaussian surface of the curved surface. Now the cylinder is a Gaussian surface which is normal to the boundary. Cylinder surface is a normal to the boundary, such that one face of the medium 1 and it ends into the second surface of the medium 2. First one surface will be starts and another surface will be ends of the second medium. ds is a small area of the cylinder. In this cylinder having a small surface area, ds has such area and each end. No free charges will be obtaining inside of the Gaussian surface. This inside of the cylinder there is no free charges will be available. Applying Gauss law in the dielectric medium displacement vector D in a cylinder, the total electric displacement through a Gaussian cylinder is written by, already we know about that, surface integral of the flux of the displacement vector D1 cos theta 1 and integral surface integral of D2 cos theta 2 into ds plus electric displacement through the side surface will be equal to 0. So next, but inward flux will be negative and outward flux will be positive. Inward flux will be negative and outward flux will be positive. Therefore, flux through the curved surface is negligible. Therefore, the minus integral of surface integral of d1 into cos theta 1 into ds plus integral surface integral of d2 into cos theta 2 into ds, which is equals to 0. So this negative term will be comes under the equation to the other side, which becomes in positive. Now we will get surface integral of d1 cos theta 1 into ds, which is equals to surface integral of d2 cos theta 2 into ds. Therefore, this equation integral terms will be cancelled, Finally we will get d1 cos theta 1 which is equal to d2 cos theta 2. This term we call it as an equation 1. This equation 1 shows that the electric displacement d passing from one medium to the another is same and electric displacement is independent of the medium. Next, now we'll come to the second boundary condition of E, electric field vector E. Here we find out boundary conditions of the E obtained by considering work done by taking a unit charge around a small rectangular place. Unit charge surrounding a small rectangular length. Rectangle having a small length. Rectangle having a small length dl and it has a negligible height. This rectangle having a negligible height. The length of the rectangle is parallel to the boundary separating between the two medias at absolute permittivity epsilon 1 and epsilon 2. The medium 1 has an permittivity epsilon 1 and medium 2 has an epsilon 2. The rectangle will be parallel to between the two mediums of the boundary condition. The electric flux or field E1 is the electric flux or the electric field V enters at the from one side E1 at theta 1 of one surface, first surface, and this surface electric field intensity will be emerges out into the second surface, which makes an angle theta 2 from the second surface. The work done is taking unit positive charge. The work done is taking unit positive charge around the rectangle PQRS must be equal to 0. Therefore, this will get the line integral of E into dl, which is equals to the sum of integral of from P1 to Q from the limit E into dl plus Q integral of Q to R into E into dl plus surface line integral of R to S E into dl plus surface line integral of S to P E into dl, which is equals to 0. The length of QR and PS will be small because the line integral is neglected along them. Therefore, E1 into sin theta 1 dl minus E2 into sin theta 2 dl, which is equals to 0. Therefore, here dl and dl, this equation dl will be common and we will getting the equation E1 sin theta 1 is equals to E2 sin theta 2. This we call it as an equation 2. The tangential components of the electric intensities are the same on two sides of the boundary surfaces. Therefore, the relationship between D1 and D2 in the equation 1 is given by D1 cos theta 1, which is equals to D2 cos theta 2. We knowing about that D is equal to epsilon into E. Therefore, D1 is equal to epsilon 1 E1. D2 is equal to epsilon 2 E2. Therefore, we will know that the epsilon is equal to epsilon naught into epsilon r, which is equals to epsilon r in epsilon naught into epsilon r remains K. Our relative permittivity of the dielectric constant. So, epsilon will be changes into the this equation. We will getting the epsilon 1 E1 D1 will changes into epsilon 1 E1 cos theta 1 and epsilon 2 D2 E2 cos theta 2. Epsilon 1 here we will changes into epsilon naught into K1 E1 K1 cos theta 1 epsilon naught E2 K2 cos theta 2, and this will be getting epsilon naught and epsilon naught will be cancelled. Finally we will get E1 K1 into cos theta 1 is equal to E2 K2 cos theta 2. Now we dividing the equation 3 by equation 2, we will get the E1 K1 cos theta 1 dividing by E1 sin 1 E1 of sin theta 1, and which is equals to E2 K2 cos theta 2 dividing by E2 sin theta 2. Here E1 and E1 cancel, and right hand side E2 and E2 cancel. We will get K1 cos theta 1 dividing by sin theta 1, which is equals to K2 cos theta 2 sin theta dividing by sin theta. Here K1 remaining same, and sin theta 1 by cos theta 1, sin by cos is known as an tan, sin by cos is known as a tan. Therefore K1 by tan theta 1, which is equals to K2 by tan theta 2. By cross multiplying this equation, we will get K1 tan theta 1, which is equals to K2 tan theta 1. We will get the K1 by K2, dielectric constants of the K1 first and the second medium is the relationship between tan theta 1 by tan theta 2. This is the relationship between the electric displacement vector D and E of the boundary conditions, that is K1 by K2, which is equals to theta 1, tan theta 1 by tan theta 2. Thanks for watching.